Okay, so hi everyone. So my name is Daniel Ahmed, and I'm an assistant professor of acoustic robotics for life science and healthcare in the mechanical and process engineering at ETH. So my goal is to develop like macro scale nanorobotics, and the way we do it, we use ultrasound to drive it. The big picture is like, can we use this robotics so that we can navigate inside the body, and so we can target specific diseases such as like cancer, and then we deliver the drugs locally into the tumor sites. So that's one of the main objectives. But of course, like at a certain particular frequency of the ultrasound, these robots will start to move. So you have this control, or you have this specificity by which you can manipulate these robots via ultrasound. And I think one of the reasons that I'm focusing on ultrasound is mainly because like ultrasound is a system, or that you see ultrasound imaging exists in almost all hospitals in developed countries and in developing nations. So my goal is we want to establish a robotic platform, a micro nanorobotic platform, so that it can be used not only in developed nations but also in like developing countries. So we have developed various types of micro acoustic-based robots. Maybe I can show you two, three types of acoustic robots. Is that fine?
Yeah, please do.
Yeah, so basically what we did, so first we developed these micro robots using this two photolithography using our microscope. So these are the micro robots that you see. So base and inside you see this dark color cavity. So the goal is to trap a microbubble. And based on where you trap a microbubble, you can get linear motion, rotational motion, and directional motion. So here is a swimmer where you can see at the center, you see this microbubble. And what we try to do, we try to actuate or excite this microbubble using ultrasound. And what we observe at a certain frequency, that is the resonance frequency of the microbubble, these microbubbles start to oscillate at a very high amplitude oscillation. So this is an oscillation of the microbubbles. These images or this video was captured using a high-speed camera at 0.5 million frames per second. And then when we release this micro robot, you can see they start to propel very fast. I think the video is clipping, but here you can see much more.
Yeah, I can see it.
Again, these are captured using high-speed camera, but we need to slow down to 24 frames per second. And depending on where you trap this microbubble, if you trap it at the center, you get a linear motion. If you trap it off center, you get this rotational motion. And then, so one of the biggest challenge of ultrasound-based robotics or any sort of robotics, how do you navigate microrobots in the vasculature? Because typically what happens when you inject any particles in the blood flow, it will follow the stream. It's almost impossible to control, right? So what we try to do, we try to develop a device strategy by which we can actually manipulate these manipulator microrobots in the vasculature or against the blood flow. So we got inspired by this nature's microswimmer, for example, the sperm cells, the bacteria. So what they do, the sperm cell or the bacteria, they can actually execute against the flow. And the way they do it, they move towards the wall. This is the wall, and at the wall, you have zero velocity. So they very cleverly feel that they have a zero velocity, and then they can actually, if the flow is zero at the wall, they can actually turn against the flow and move against the flow. Here I show how I control the storm in acoustic field. But here is a result. So initially we create this storm, so they are moving with the flow. So you can see, so they're moving from right to left. And then let's start the video. It's moving. Then here I apply ultrasound. And as I apply ultrasound, they become trapped here. So it's almost like mimicking a neutrophil before transmigrating to a disease site. And then here is another video. You can see, like, as soon as they hit the wall, so this is the wall, they can actually move upstream. And here is another video. You can see this this almost like this storm. They can actually move against the flow, and you can see the particles are moving in this direction. For cancer, but you realize this technology can also be used to, like, for example, if someone has a stroke or you have a blood clot, it can also be used to like unclog those places. I think
that makes sense.
There are a lot of opportunities that we can do with our technology.